today's lecture we will discuss about the microplates. Various structures and features of MEMS. Plates are square, rectangular, solid, porous, single layered and multi-layered. Depending upon the application requirements, they are designed and subsequently used. The effective area of the plate range from few hundred to thousand micrometer square. One application of microplate is to build parallel plate capacitor. In particular, a voltage tunable parallel plate capacitor has two movable parallel plates. Using electrostatic method, one can move the plates. Typically, capacitance of the tunable capacitor can vary from 1 pf to 2 pf, corresponding to applied bias voltage from 0.5 volt to 3 volt. Coming to the types of microplate, the first one is the diaphragm, in which we will discuss about its structure and theory. At macro level, diaphragms are thin circular plates broadly used for the measurement of both low and high values of pressure, force or load. The principle is based on deflection. The displacement d is proportional to the applied pressure, force or load as shown in the figure 5.4. The pneumatic fluid and acoustic applications use diaphragms. The mathematical deflection formula can be written as follow, where displacement d is given by c a square f by t cube, which is equivalent to k into f, where f is the force or pressure or load applied, k is the constant depend upon the type of the diaphragm. So A and T are the radius and thickness of the diaphragm respectively. C is a constant which depend upon the Poisson's ratio and the Young's modulus of the material from which the diaphragm has been made up of. So considering C a square by t cube as a constant k. K can be defined as sensitivity of the transducer. The above equation can be written more precisely. The deflection then can become dr is equals to pr to the power 4 divided by 64k multiplication the bracket of 1 minus xr by r whole square to the raise whole square. Here in this equation, p is the applied load, xr is the radial coordinate, r is the diaphragm radius, k is a measurement of a stiffness, which is given by k is equals to et cube divided by 12, 1 minus v square, where e is the Young modulus, t is the plate thickness and v is the Poisson's ratio. So these are the material property from which the diaphragm is made up of. Coming to the another diaphragm type, this is the corrugated diaphragm. In order to improve the sensitivity, corrugative diaphragms are designed. This is one of the diagram shown here. You might have seen the capsules for bellow measurement. So these are called capsules and bellows. Bellows have more sensitivity than the capsules, although their application domain vary. The material used for diaphragms are nickel, phosphor, and stainless steel. In many pressure sensors, strain gauges are mounted on the diaphragm. These are called strain gauge based electrical output pressure transducer. The change in pressure is related to the strain in the diaphragm. Sometimes the diaphragm itself is made up of semiconductor and the strain gauge is doped within the diaphragm at the time of manufacturing. Such types of transducers are intended for the measurement of absolute pressure. Pressure with respect to vacuum we can measure by using such devices. Capsules and bellows are broadly macro level devices. Micro level designs are also possible. Now coming to the deflection formula for MEMS, that means micro level diaphragm. The design criteria, that means the thickness and radius, fabrication method, that means material selection, surface and bulk, and application areas, that means absolute pressure or acoustic pressure, etc. of MEMS diaphragm significantly differ, although the physical principle remains same. That is, deflection is proportional to the measurand. Quantitatively, the deflection theory and characteristics of micro machine diaphragms is not same as that of large deflection theory and characteristics. At micro level, that means for micro machine diaphragms, it is assumed that the applied load is constant over the diaphragm surface. In contrast to the deflection equation mentioned in equation 5.3, the previous equation which we have studied, the deflection equation in case of MEMS is given by dr is equals to pr square divided by 4 sigma I t with a bracket of 1 minus xr square by r. Here sigma I is the intrinsic built in stress of the plate diaphragm. The diaphragms are manufactured in various shapes and sizes depending upon the nature of transduction signal at hand. Most commonly, diaphragm shapes are either circular or rectangular. However, the thickness in a particular type is constant and usually less than 10 micrometer. The development of high performance micro diaphragm structure is critical in the micro manufacturing process. The diaphragms should provide linear relationship with regard to deflection and applied pressure. Making diaphragm thinner can increase the sensitivity, but for high pressure applications, the thin diaphragm produces nonlinear responses. It is also important to characterize the relationship between diaphragm thickness, deflection, and sensitivity. That can be done at both analytically and experimentally prior to its design for real-time applications. The analytical analysis primarily provides appropriate guidelines for the design of micro diaphragm based sensors. So coming to the another diaphragm type, that is the piezoresistive measurement. CMOS based ultrasonic MEMS diaphragm is used for fault detection. by sensing the echo of an ultrasonic burst in a structure. In such application, acoustic impedance of the diaphragm is exploited. Acoustic impedance is defined as the ability of a diaphragm material to transmit sound. The diaphragm is integrated with other elements such as piezoresistor, which is built in CMOS polysilicon layer. The piezoresistor behaves as a strain gauge through which piezoresistive sensing is achieved. The change in resistance is taken as readout and is produced through a balanced bridge circuit. The bridge circuit can also be fabricated in the same substrate. The output of the bridge circuit is fed to the instrumentation amplifier. It is to be noted that the acoustic impedance of the diaphragm is always less than the medium, so that the piezoresistive implanted strain gauge diaphragm will be able to closely track a displacement due to a sound wave. Optical and capacitive based sensing mechanism can also be employed in the diaphragm sensors. Another type is freestanding diaphragm. There is another structure of diaphragms called freestanding diaphragms, which possesses high sensitivity, that is, the ratio of output to the input is high. Fabrication of freestanding diaphragm, as shown over here, is required for the design of micro mirrors. I hope you remember that micro mirrors we have discussed in another unit already. Micro mirrors have application in display technology and optical switches in telecommunication industry and consumer product arena. Moreover, these devices find their applications as tunable filters, microcavity and wavelength sensitive detectors. Using a wet chemical etch and a release process, freestanding diaphragm structures can be fabricated. Electrostatic actuation to the freestanding diaphragm is possible for tuning applications in optical transmission systems because of the formation of a cavity by the membrane and the substrate surface. Now, in the upcoming lecture, we will discuss about the piezoelectric material in sensors and actuators.